Okay, so let's apply this then. Okay, so what we are seeing then is that the angular momentum, which is integral over omega t rho v d little v, is integral over omega t rho. Now let me write the arguments. Okay, we're going to write v as g dot function of time plus omega hat, remember omega hat is a function of time, cross x minus g d little v. Okay? Right? So we get integral over omega t rho x comma t g dot t dv plus integral over omega t, okay, rho x comma t omega hat crossed x minus g dv. Okay, right? Okay, so what we're seeing here then is that this quantity is basically, this quantity can be written here because g dot is a function of time alone, right? We see that this integral here can be written as we have rho integrated over dv, right, which gives us the total mass, all right? And I think we have not yet used a symbol for mass, but let's just use little m because we're using d little m as the elemental mass. Okay, so here we have mg dot, right, plus okay, so now let's look at what else we get here. Okay, so what we're seeing here is that the total linear momentum here, omega hat, is a function of time alone, right? So we can write this term, write the second integral as omega hat function of time, right? And here we remember the g dot is a function of time as well. Okay, so we have omega hat function of time crossed integral of omega t rho function of x comma time x minus g d little v. Okay, but you remember the result that we proved on the previous slide, 2 slides ago, up there at the very top, okay, saying that the integral of rho x minus g dv is 0. We invoke that here, okay, and we are seeing that this contribution goes to 0. Okay, right? So what we are seeing here is that the linear momentum of a continuum body of undergoing rigid motion is essentially the mass of the body times the velocity of the center of mass. Okay? As far as linear momentum is concerned, this rigid body, even though it has mass distributed, is essentially acting as a particle. Okay? All right, so this is our result for linear momentum. Okay? Since we're here, let's just go ahead and see what happens here if we take another derivative and write out the rate of change of linear momentum. Okay? There are 2 ways we can go about it. We could either go through the process of the integrals, or we can work directly from here. All right? So let's just work directly from here. What we will see here is that L dot as a function of time is equal to m g double dot. Okay? Simple enough, right? And this, of course, is going to be equal to the total force on the body. All right? So what this says is that now, for this body undergoing rigid motion, right, even the rate of change of the linear momentum of the body, right, which of course does not account for these types of tumbling motions, right? It is simply the rate of change of linear momentum of the whole body acting like it was a particle at the center of mass. Okay, and the net effect of the distributed forces on the body essentially is to accelerate the center of mass, long as we're talking only of linear momentum and forces. Okay, right? So in this sense, when we talk of linear momentum, we don't get any, we don't see any effect of the fact that the mass is distributed, and in fact those different particles are undergoing a further rotational motion. Okay, that's lost in when we look at linear momentum. Okay. So the conclusion that we can draw from these two is that linear momentum and its rate I'm going to say that you can think of applying those notions to the center of mass. Okay? All right. Let's move ahead now and look at what happens with angular momentum. Okay? So, for angular momentum, J naught as a function of t is, so we're talking here of angular momentum also of rigid bodies, right? Okay, so the definition for angular momentum of this rigid body is going to be integral over omega t of rho, function of position and time, x cross the velocity. Right? That's the general definition. All right? And in this case, what we have is that for the velocity, we have this special way of writing it out. All right. Now, I am going to play another one of these dirty tricks here. What I want to do is to rewrite the position little x by expressing it as a position of the center of mass and position relative to the center of mass. Okay? So, what I'm going to do is write integral over omega t rho x and t multiplying, okay, I'm going to write that x cross all the other stuff as g plus x minus g, okay, all of that cross g dot plus omega hat cross x minus g. All right. Okay. And now when we pull things together, we will observe that we can write these integrals, this out in the following form. We have rho. I'm going to suppress the writing of arguments of rho. Okay, we just remember that it depends upon x and t. So we have one term which is rho g cross g dot. Okay. Plus rho g cross omega hat cross x minus g. Okay, and that was obtained by applying okay, the terms I've carried out are this one first, that is rho g cross g dot. The next term I wrote out was g cross that. Okay, and now I'm going to do x minus g cross this. Okay, so I get plus rho times x minus g cross g dot, and finally I get rho times x minus g crossed with omega hat cross x minus g. Okay, all of this integrated over dv. All right, and that last term is this one. All right. Okay. Okay. Now let's look at things. In the case of the very first term here, this term, okay, observe that g and g dot are not functions of position. Only rho is a function of position. But rho, when integrated over dv, gives us the mass. Okay, so this first term, when we carry out the integral, is going to give us m g cross g dot. That dot went a little too high. Right, and these are vectors. Right, and what we are seeing there is that g is the position of the center of mass, so that term is really the sort of the position of the center of mass crossed with mg dot, which is the linear momentum of the center of mass. Okay? What about the next term? Look, observe that the next term has these two factors which have spatial dependence. G is a function of time alone, and omega hat, being the angular velocity, is also a function of position alone, right? Because it's the angular velocity of a body that's rigidly moving, right? So the angular velocity is about the center of mass, is sort of fixed, right? It's not a function of position. But that is being integrated over dv, right? And remember the result we derived for this type of an integral. Okay? This term equals 0, right? Because we have rho times x minus g integrated over dv, and that we proved back here. Yeah, the second equation, the second line of this slide, right? That we proved is equal to 0, right? So this term is equal to 0. For the same reason, this term also is equal to 0, right? Let me not use this. Let me use arrows here. Because of, well, because of this term here, right? That integral rho x minus g dv is equal to 0, but then g dot is just a function of time, so it comes out of that integral. Okay, so this term also equals 0. Okay? All right? For this term, what we're seeing is that we have one cross product of omega hat cross x minus g, and then we have x minus g coming along from the left and being crossed with that cross product. Okay. Now there is a standard result for these for the cross product of a cross product, right? And that result is that we get rho times we have x minus g dotted with x minus g again, but then that is x minus g Euclidean norm square times omega hat, okay, minus x minus g tensor x minus g acting on omega hat, okay, and we have rho multiplying all of that. Okay, so observe that the first term here is a vector because we have a scalar x minus g Euclidean norm square multiplying omega hat, and here too we have a tensor which is x minus g tensor x minus g, sorry, and I should put parentheses around these two. Okay, so we have that tensor formed as a dyadic product acting on another vector omega hat, which gives us also a vector. Okay, so when we collect terms from here, what we see is that we get for j naught dot as a function of time, we see that it is we have one term which is the angular momentum of the center of mass. Okay, so this term is the angular momentum of center of mass. The next term that we get is integral over omega t of rho multiplying, I'll just carry over the term that we had on that last term that we had. Okay, all right. What I'm going to do here in this last term is observe that omega hat t is a vector, and it appears in both those terms. It appears, like I said, in both those terms, but since it's a function of time alone, I can pull it out of the integral. Okay, and in fact, I'm always free to squeeze in here the isotropic tensor. Right? It always comes along for free. Okay, it doesn't change anything. What this lets me do then is to write out our right-hand side as the angular momentum of the center of mass plus an integral over omega t rho times x minus g Euclidean norm square isotropic tensor minus this dyadic product, right, or the tensor product of x minus g with itself. All of this integral dv times, or not, sorry, not times, but acting on the vector omega hat. Okay, because omega hat is a function of time alone, and I can pull it out of the integral. This quantity here is a tensor, right? I should be clear because the first term is the isotropic, second order isotropic tensor, and the next term is a tensor product of two vectors, which is also a tensor. This tensor has a special name. It is what we call, first of all, we're going to denote it as a special J sub G. Okay, it is, do you recognize it? Do you know what this thing is called? it is the moment of inertia tensor. Okay, so this is the moment of inertia tensor, and the reason for the sub little g is to remind us that this is the moment of inertia tensor obtained when we are computing the moment of inertia about the current position of the center of mass, right? So it's the moment of inertia tensor about g, right, which is the current position of the center of mass. All right? Okay, so finally we have J naught dot is a function of time, right? Sorry, I realize I've been making this a J naught dot. It really is just a J naught. Sorry. Should probably go back a slide and check what I did back there. No, it was okay on the previous slide. It was only when I came over here that I made a J naught dot. Okay, so it is really just J naught. It's just the angular momentum. Okay, so like we said, it's the angular momentum of the center of mass plus this the angular momentum about the center of mass. Okay, so this is the angular momentum about g, right, which is the center of mass. All right, so what this is saying now is that rigid motion, we have this body tumbling, right, and it's doing something like this. The total angular momentum is the angular momentum of this body as if it were just, so it's doing this sort of a motion. So we can compute the total angular momentum as if this body were just moving without tumbling about itself, right, but we're moving about the origin, right, something like this. That is the first term in the final equation, right? In addition, there is a further component of angular momentum which comes about from the fact that the body is tumbling about its center of mass. Okay? And that just comes from the fact that we've decomposed the motion in these two forms. Okay? Okay. To round off this segment, I just want to state that a tensor of this particular form, right? The particular form that appears here, okay, that has a name for to itself, okay, and whenever we get something of the form integral over omega t rho function of x comma t x minus g tensor x minus g dv, we call it this thing is also called the Euler tensor. Okay, it's the Euler tensor sort of relative to g, relative to the position of the center of mass. Okay, that's one thing to note. And the other thing I want to point out is the following fact. Note that, so consider Jg, which is integral over omega t rho x minus g Euclidean norm square isotropic tensor minus x minus g tensor x minus g. Right? Use the fact that x minus g we showed early on when we rewrote the motion as the motion of the center of mass plus rotation about the center of mass, translation of the center of mass plus rotation about the center of mass. We showed that this is q reference position minus reference position of the center of mass. Okay? Now, when you make the substitution in there, what you will be able to show is that Jg, okay, also given that Q equals a function of time alone, right? So Q has no role to play really in this in the integral, right? You can pull it out of the integrals. Okay. When you do all of this, what you will see is that Jg can be written as let me see, yeah, written as Q J capital G Q transpose, okay, where J capital G is now, essentially it turns out to have the following definition. Integral over omega naught rho 0 function of x Euclidean norm square of this vector, right, isotropic tensor, minus the tensor product of the reference position of every point relative to the center of mass with itself. Okay? It's not very difficult to show. You just make that substitution that I have here, right? And use the fact that whereas the integral for this definition of the moment of inertia was an integral over the current configuration, we can always do a change of variables and write it as an integral over the reference configuration. Okay? So what this tells us is how, when we're considering the moment of inertia of this point, right, here, about the moment of inertia tensor of this point here about the center of mass, okay, how to relate it to the moment of inertia tensor that we would compute about another point here, okay, which would have been the original position of the center of mass. Okay? All right. I think we're going to stop here.